Sockwell, though some of you may know me better by my username code sections. And this talk is entitled 105 C++ algorithms in one line of Raku each. Now, in addition to being a Raku developer, I'm also a lawyer, and I feel the need to say that this talk title should really have a few asterisks by it. The 105 number comes from the algorithms header in C++. This talk will walk through most, but not all of those 105, plus a few bonus ones. So I think the 105 is still about right numerically, but may not be 100% accurate. On C++, as I said, most of these algorithms are drawn from the C++ algorithms header, but some of the bonus ones are not from C++, so there's a slight footnote there. And then on the one-line business, there's a slight footnote in that although all of these can be done in one line of Raku, for the purposes of formatting, I've split some up on the slides. But with all of those footnotes out of the way, I want to start with a basic question. Why am I giving a talk about 105 C++ algorithms in one line of Raku? In a lot of ways, I'm giving this talk because it's a talk that I wish I could have seen when I was first starting to program Raku a few years ago. When I first started learning Raku, there were so many language features I loved, but there were also times when I would reach for a function from the standard library from Rust or some other language I'd programmed in and not be able to find it in Raku and conclude that Raku just was missing some functionality that I was used to. To give an example, I really clearly remember this happening with the Rust function FilterMap. So for those of you who may not know Rust, the FilterMap function allows you to iterate through a collection and then either filter an item out of the collection or keep it and transform it in some way. And it does that in one pass so that you don't need to iterate through the collection twice. And I searched the Raku documentation for an equivalent function and didn't find one, and concluded, like, oh, well, Rust is really focused on low-level performance. Raku is a higher-level language, so maybe it's okay in Raku to just map over a collection and then after you've transformed all the elements, filter out the ones you don't want with grep. And like, yeah, you end up iterating over the collection twice, which has some performance cost, but probably not that big a deal if you're not doing something super performance sensitive. And I thought that's just the way it was. And then a little while later, I realized, wait, hang on. It's not that Raku doesn't have a filter map function because it's not worth including that functionality. Raku doesn't have a filter map function because it doesn't need a separate function for that, because we can already do that in Raku with map. All we need to do is use the Raku primitive idea of empty, or a slipped empty list, and combined with map, we can iterate through the collection with map. If we want to keep an item, then we can transform it in some way and with a function. And if we don't want to keep it, we can just return empty, which has the effect of excluding that item from the return value. And as an aside, that it has some interesting sort of type theory implications for Raku's map, in that it is not what a functional programmer would really call map. It's not guaranteed to return a list of the same type, a list of the same length. But that's an aside. The point here is that there was functionality that was entirely built into Raku, but that I didn't know about as a beginning Raccoon, because I was looking for a filter map equivalent, and there is no function that is the equivalent of filter map. It is just an emergent item, an emergent piece of functionality that comes naturally from a combination of some really good primitives that Raku has built into it. And there are a tremendous number of features like that in Raku, and I started thinking, maybe if only there were a list of those features, it would be very helpful to me. And ever since then, I've been thinking, like, one day I'm going to give a presentation that collects some of those sort of hidden, emergent pieces of functionality. I got started with this presentation by thinking about what I would have wanted when learning Raku, but I also know that I am not at all the only one who could benefit from this. Literally on the day that I was finishing this presentation up, I came across a comment posted to GitHub by someone who's new to Raku, and I have the screenshot here where the only thing I've changed is the user's screen name. And they said that they were new to Raku and liked some things, but were confused because they couldn't find simple statistical functions like mean or standard deviation. Now, I have two thoughts about that. First, it is absolutely true that there is no average or mean function or method built into Raku. Second, it is absolutely true that we don't need an average function built in, because we can compute an average just by taking the sum of a list of numbers and dividing that by the length of the list. And doing that is better than having an average function. It's better because it actually takes fewer characters to write, and it avoids any ambiguity about, is this average as in an arithmetic mean or a geometric mean or a median. What exactly this code is doing is 100% clear in a way that wouldn't be true if we had a .average function. However, it does lead to this problem where someone searches our docs and says, hey, what's up with this language that says it could be good for math, but they don't even have an average function? So people, every day there are new raccoons who come to the language and think that we're missing features that we're not. And so part of my goal with this presentation is to sort of lay out how some of these common pieces of functionality can be achieved just by combining primitives such as sum and taking the length of an array just by casting it to a number. More specifically, I have two goals for this presentation. First, I want to actually teach the specific patterns that are required for the 105 functions I'll be walking through. I want this talk to be a resource where you will come out of it knowing what Raku primitives to reach for to implement each of these functions. But perhaps even more importantly than that, I hope that this talk can be a way to build intuition for the ways in which Raku primitives can be combined to implement different functions in line and in a single expression in a way that replace or remove the need for some things that might be built-in functions provided by the standard library of some other language. And I think that is actually the more important objective here. As long as a list of 105 algorithms might seem, it isn't everything. And I think the intuition is even more important than the specific details. Before getting started, though, I want to address the question of why C++. I mentioned that I came to Raku from Rust, and have really never been a C++ developer. So why am I talking about C++ algorithms instead of ones from Rust or JavaScript or Perl or any other language I could have picked? Well, partly it's because of a few different reasons. C++ has familiar syntax to people who know C family languages. It also has a rich standard library that gives a lot of algorithms to work with and draw on for this talk. But it's also because I'm somewhat riffing on a really excellent talk titled 105 STL Algorithms in Less Than an Hour. And I really recommend that you watch that talk, but I'd actually like to play you an excerpt from it right now.
What we're going to talk about today is the STL algorithms. We're going to start off this talk with a question to you. Who in this room is aware of the fact that it's a good thing to know the STL algorithms? Just raise your hand if you're aware of that fact. That's pretty much everyone hands rising. That's pretty cool. Second question, who knows them all? Raise your hand. Come on then. That's pretty much that's actually no one's hands rising now. That's exactly the purpose of this talk. When you walk out of that room, you will know every single thing that's in the STL algorithms library. To do that, I suggest that we start with a brief chat about why it's important to know them and what to learn in them, and then we dive in the STL algorithms themselves. All right? So there's this thing that's been popularized across the C++ community over the past few years. That's we need to know all the STL algorithms, and we need to know them well, very well. But why? Well, for one thing, they can make our code more expressive. And they do that by raising levels of abstraction, which means that they allow you to express what we want to do as opposed to how we want it executed. And I think that raising the level of abstraction is one of the most efficient ways to write expressive code. And it can be sometimes spectacular. Like if you've seen that talk a couple of years back by Sean Parent, which was called C++ Seasoning, in that talk Sean took a chunk of code that was a bit hard to understand, and he refactored it into a more concise and expressive piece of code just by picking the right STL algorithm.
Now, I am absolutely all for writing concise and expressive code, but I want to push back on part of what he said. He just said that one of the best ways to write expressive code is to raise the level of abstraction. And I disagree, or at least disagree that that is nearly always the case. Aaron Hsu has a phrase that, I don't know if he coined it, but it's where I first heard it, transparency over abstraction. And I think that there are many times where software developers reach for abstraction prematurely and use abstraction, and particularly black box abstraction, where the implementation details are hidden away, as a way to hide away details that actually aren't irrelevant, that actually do matter. So, to go back to the average function, yes, that is an abstraction that can be helpful, but if it isn't clear to the caller what that is doing, whether it's taking the mean or the median, then that can be an abstraction that is confusing. Whereas if you have transparent, where we're adding all of the elements and we're dividing by the number of elements, you know exactly what that's doing. That level of transparency is extremely helpful. And I think actually far more expressive than the black box abstraction that just hides that away. I think that expressive code is excellent, but I care not just about expressiveness at the call site, but expressiveness of the entire code project as a whole. So if there is code that reads very cleanly at the call site, but causes a programmer who's debugging it to need to use IDE or editor function where they're constantly jumping to definition to say, oh, well, I see this function, but I don't know what it does, and I need to know what it does. So I'm going to jump to the definition of that function. And then that function calls 5 others, and I need to know what they do. And so I'm going to jump to definition there. That is a time where abstraction has not made the code clearer. It's made the code more confusing and less expressive, and that the code clarity would have been increased by using transparency rather than abstraction. So in a lot of ways, that's sort of the hidden thesis of this talk, is that not only is it fine that Raku doesn't have some of these functions that C++ or other languages might have in a rich standard library, it's actually better that we as raccoons get that functionality by combining primitives, because it gives us a less abstract and more transparent way to achieve that same functionality. We can, in a line of code that is no longer or barely any longer than a long function name, can see exactly what is being done and don't need to have that jump to definition abstraction penalty. So that's something I'd like you to keep an eye out for as we go through these examples. Keep an eye out for places where the functionality is where the C++ name might not be clear, where you might have some abstraction that, yes, hides away details, but that just from the name, without checking the documentation, you wouldn't necessarily know what is going on. And take a look at the corresponding Raku code that we'll be walking through and say, could I know what that code is doing in a way that I wouldn't with the more abstract version? And I hope that you'll end up agreeing with me that there are many places where that abstraction is over abstraction, and where the transparency provided by the Raku expression results in code being clearer. The first function I want to start with is actually one of those bonus ones I mentioned that is not from the C++ algorithm header, but it's one that is probably familiar to any of the functional programmers in the audience, and it's one that will be very helpful to us in implementing some of the other C++ algorithms. So I thought it would be an excellent place to start, and that is Ziptail. That is a function that takes a list and returns a new list that is comprised of each element in the original list paired with the following item in the original list. So if you had the list 1, 2, 3, Ziptail would give you back a list containing the pairs 1, 2 and the pair 2, 3. And by pair, I don't mean the Raku data structure pair. I mean a 2-element sublist. So implementing this in Raku is very easy. The most straightforward way would be to just take a list and zip it together with a version of that list containing items starting from index 1 all the way to the end of the list. I actually prefer a slight variant on that instead of using array indexing to index into the second list, just says what we want from the list is, for the right-hand side of our zip, is the original list skipping the first element. So here, a.skip. The only problem with this implementation is that we're repeating the reference to our array A, which is not a problem for expressiveness there, but if we were using a longer name, then repeating that longer name on both sides of the zip expression would be a little bit cumbersome. So my actually preferred spelling for Ziptail is this one here, where we are using an anonymous method to say we want to start with a list and then take that list and zip it together with that list, having skipped the first element of the list. To me, that reads very expressively and says exactly what we want to do with Ziptail. There is a different spelling for Ziptail, which uses the .rotor method. So you can say we want to take a list and rotate it into batches with 2 elements each and a -1 element gap between each batch. A -1 element gap, of course, means a 1 element overlap. And that gets you exactly the same thing. I don't like that spelling quite as much because it's not as expressive in terms, it doesn't encode the idea that we're zipping together anything, and it is also slightly longer, and I really like the anonymous method syntax, and it's something that will come in handy in several of our other implementations that I'll be going through in this talk. So I want to start with that and go ahead and introduce that, and I'll be using the anonymous method Ziptail implementation as we go forward, but I do want to mention the rotor one in case you come across that spelling. Similarly, the next function I want to talk about is also a building block that is not from the C++ algorithm header, but that we'll use in implementing functions from it, and that is just useful on its own right. And that is a binary filter. That is, if you have a list A and you want to filter items in or out of that based on some binary predicates that you have in list B, then binary filter is the way to do that. So let me walk through the implementation and then also an example, since that is a little bit abstract to describe. So if you have, so the way we implement this is very simple. We just use the hyperoperator to AND together each element of the binary predicate list with the list of interest. So if the list that we are interested in, it contains foo, bar, baz, and buzz, and we have a binary predicate list of true, false, false, and true, then we can apply that and AND them together with the hyperoperator, apply our binary predicate, and get foo, false, false, buzz. Note that if we don't want to get the falses in there, we can, of course, grep over the resulting list and exclude anything that is false and end up just with foo and buzz. If you are confident that your list does not have any falsy values, then you could simplify this grep and just look to keep truthy values. Here I'm only excluding things that are literally false rather than falsy, but which is the more general approach. But if you are confident of that your list A did not have empty strings or zeros or other falsy values, then you could simplify that grep a bit. Okay, now let's dive into some functions that actually are in the C++ algorithms header. We'll start off very easy with functions that from the algorithms header that do appear in Raku, but that have a different name, and thus you might not find in the Raku documentation if you are searching for them under their C++ name. So, for example, in C++ you can shuffle a vector, an iterator, and in Raku you can pick all of the elements from a list or an array, which provides equivalent functionality. You can, of course, pick a smaller number and get a smaller number of random output, but if you want the entire list in random order, you can pick everything. And then equal is perhaps even more directly equivalent. We have equiv or a few other equality operators, but equiv is the most direct to C++'s equal. We have the much more concise comparison operator, which is the equivalent of C++'s lexicographical compare. I'm not sure if comp is the right way to pronounce that. That's how I say it in my head anyway. Next, and still very firmly in the easy camp, we have a group of C++ algorithms that are the equivalent to Raku's junctions. All of is equivalent to our all junction, any of equivalent to our any, and none of our none. Junctions in Raku, of course, have a variety of superpowers and will have an increasingly large variety of superpowers as auto-threading continues to be further developed according to the specification. But even in their most basic level, they can at least serve as equivalents to all of, any of, and none of from languages like C++. A few other easy aliases that I don't have a whole lot to say about. Finding an element in C++ is like looking for the first element in Raku. And of course, with our first, you can get either that element as a pair of its position in a list, or just as the value, if that's what you want, or as a two-element list of the key and the value with the PV or KV named argument, respectively. Our equivalent of C++'s min element is min. Our equivalent to max element is max. And our equivalent to min max element is min max. And one that is you get no clue, no points at all for guessing our equivalent to their unique is unique, which may be uniquely the only time we have exactly the same word that C++ uses. Now we're getting into some of the functions from C++'s algorithm header that, while we're still essentially in alias territory and haven't gotten into the heart of what I want to talk about, we're at least getting to a point where I have something to say about these algorithms. So we handle both sort and stable sort with our sort, which it defaults to being stable. So that is one area where we don't have a direct equivalent to an unstable sort. There are ways you could do that, but this is more of the high-level nature of Raku showing through a bit. It is typically not the case in Raku that we're concerned about performance at a low enough level that using an unstable sort is helpful. So which means we're able to sort of kill two birds with one stone and use sort without having to worry about its stability. Now this next one is especially interesting because we're also able to kill two birds with one stone by handling reduce and accumulate with just our reduce. I think accumulate is an especially poorly named C++ algorithm in some ways. It is essentially just reduce, but with a default plus operator, but that can be replaced. So it basically is just reduce. And then C++'s reduce is one that has some constraints on it to guarantee that it can be parallelized. That's something that we handle, again, with a bit less abstraction by using reduce sequentially, or reduce with hyper, or reduce with race, depending on what type of parallelism you're interested in introducing. And then we don't necessarily have the same type system guarantees that the operation can be safely parallelized, but we can attempt to parallelize it and successfully parallelize anything that we can using reduce with race if output order doesn't matter, or with hyper if the output order does matter. Similarly, we can handle C++'s partial sum or inclusive scan with produce, or in the case of inclusive scan, produce paired with the appropriate parallel algorithm and a function that can be appropriately parallelized. And again, just like accumulate is oddly named in C++ by sort of encoding into the name what operation is there by default, but that can be overloaded. Partial sum encodes the idea that sum is the default operation, but produce doesn't have that encoded into the name, but you can easily supply the plus operator if you would like that to be the default operation. One thing I also have to say about reduce and produce is that they are obviously extremely similar algorithms. Reduce takes a list and iterates through it, a list or an array or other iterable collection, and iterates through it and applies a function to build up an accumulated result, and then returns that final single value. And produce does exactly the same thing, but it returns a list of all of the intermediate values being produced along the way. In many functional languages, these are known as reduce and scan, or sometimes fold and scan. And what I dislike about those names, even though admittedly fold and scan are shorter than reduce and produce, is that those names don't have any indication that the algorithms are so similar. Reduce and produce just sound similar, and that's something that I love about Raku, is that things that sound the same typically are the same. And other than APL, which uses a backward slash for produce and a forward slash for reduce, or maybe I have that backwards, I don't know of another language that so closely indicates the similarity between these two algorithms. So that's something that I've always really liked about Raku. Moving on, C++'s transform is the same as our map. Map is the normal term for that. I'm not sure why C++ went with transform. It's much longer and not nearly as commonly used. And then C++'s for each is we can achieve the same thing with our for, not a function, but a keyword. One thing that I should note about for is that, of course, Raku's for is not a traditional for with from a C family language that takes three-part iterator and everything afterwards, where you're doing I++, etc. For is just directly iterating over a loop, iterating over an iterable collection in a loop, and also notably, one of the ways that for each is used in C++ is to have an expression rather than a statement. But of course, any Raku statement can be turned into an expression with do notation. So do for can achieve the same thing that you might use a for each for, or just by wrapping it in parentheses, which achieves the same effect. So either for or for in parentheses or do for will give you a very similar output to for each from C++. Next, we come to an area where we're still dealing with aliases, but no longer aliases to Raku words, but to Raku symbols. Specifically Unicode symbols that we use for set operations, the actual mathematical symbols that are used for those. So instead of set intersection, we have the mathematical symbol for set intersection. Instead of set union, the mathematical symbol for set union. Instead of includes, we use the element operator in whichever direction you would like to, which allows more expressive code there. And then instead of the absolutely longest item in STL, set symmetric difference, we use the set symmetric difference operator. Now, I know some people would say that as concise as these operators are, that we should use more verbose and thus more descriptive names like set symmetric difference. But I would argue that there is the set of people who really know what set symmetric difference means, but who don't know that symbol is very small. There are plenty of people who don't know the mathematical symbols for set operations, but I think most of those people, most of us, I would say, who don't really work with set operations, and I'd put myself in that camp, don't really know what these terms mean either. If you're somebody who doesn't know set operations well enough to be familiar with mathematical notation for them, there's a good chance that you don't really know them. So I think that having these concise symbols in Raku not only improves the concision and readability of Raku code to those of us who are familiar with the mathematical notation, but also avoids sort of abstracting away something with a name that is just descriptive enough to be confusing. On the other hand, I think that one area where Raku is a bit confusing and its embrace of the mathematical notation is a bit confusing is with set difference, which is the one area where I will always default to the Unicode, to the ASCII representation rather than the Unicode. I know that this is a distinct Unicode character from a backslash, and I know that it is the mathematical symbol for set difference, but unless I am very clearly operating in a set context, I cannot imagine that I would distinguish that from the corresponding character for a backslash, and I cannot imagine that it would be anything other than confusing. So that is the one area where I will use the ASCII character equivalent, but everywhere else I strongly prefer the Unicode and think that it results in Raku code being much more readable for not only for set operations, but especially for set operations. So I'm glad that we have these equivalents to the set operations from the C++ algorithm header. All right, so now we're on to the last batch of algorithms from the C++ algorithm header that have direct sort of alias type equivalents in Raku. These are not ones that have similarly named functions, but ones that have symbols, not Unicode symbols necessarily, like we saw with the set operators, but symbols or other functions that provide a similar functionality. So to produce the same output as C++'s fill algorithm, you can use the list replication XX operator. It is more powerful and has more advanced use cases, but a very trivial use case of it is to duplicate the functionality of fill. So for example, if you wanted to fill a list with 10 copies of the integer 42, you would do 42xx10, which duplicates 42 10 times. Again, you can do more advanced functionality with that same operator, which I'm not getting into at the moment, but that is a trivial use case for it. Similarly, if you want to duplicate C++'s generate, you can use the sequence operator in Raku, which again, it has a more advanced use case, but a very simple way to use it is to give it a function that it will use to generate each element of a sequence, just as C++'s generate algorithm does. Next, C++ has the iota the iota algorithm, which takes a terminal value and generates a iterator up to that terminal value, 0, 1, 2, 3, 4, all the way up to but not including the terminal value. That is the exact functionality provided by the range prefix range operator in Raku. So $10 gives you 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but not 10. And just like iota, as I mentioned with the list replication operator and the sequence operator, the range operators, and it's really a family of operators, provides more advanced functionality in Raku, the ability to specify a beginning value rather than defaulting to 0, the ability to exclude or include beginning and ending elements of the range. But for just the basic iota functionality, all you need is the prefix up caret. And then on a slightly different note, but I want to mention it while we're still in this last of the freebies slide, C++ has transform reduce, but the reduce functionality in Raku is actually powerful enough to provide that same functionality with inline functions and the ability to transform your output before adding it into your accumulator. That may involve using one of Raku's sort of secret weapons of a state variable, or it may not, but regardless, transform reduce is sort of a subset of what we can handle just with reduce, and I wanted to mention that here since it is different enough to be worth calling out. All right, we're now to the point where we're actually implementing functionality ourselves rather than just relying on something being called something else in Raku than it is in C++. However, we're not to the hard stuff quite yet. So if we want to have the Raku equivalent of C++'s remove, we can just grep over a list of elements and filter out any that do not pass our predicate. So just invert the predicate that we're testing against. Similarly, if we want to count how many elements pass the predicate test, then we just grep over the list, get the passing elements, and then convert that to a number, which just gives us the count, exactly what we were looking for. Next, if we want to get a copy with certain elements replaced, map is our friend there as well. We just use the ternary operator, map over. If it passes our test, we transition to whatever new element we want to replace it with. And if it fails the test, we just pass it on through as is, and that has the effect of giving us a copy with certain elements replaced. And then find end, lower bound, and upper bound can all be implemented with the Raku function first. And depending on whether we want the lower bound or upper bound, we would need to pass the end named parameter, but that'll either find the first or the last element that passes that test. And then last and most difficult of this sort of easy batch is partition. And like with sort, Raku is going to have everything be stable by default, so we don't have to distinguish between partition and stable partition. But to implement partition, what we do is we use the classify method and pass it whatever predicate we want and then cast that to a number. So let me walk through what that does in a little more detail, because like I said, this is the first sort of more intermediate function that we're implementing. Classify will give us a hash of a hash as our output, and the keys of that will be whatever we return from our function. So here, our predicate function, which is going to return, true or false, but then we cast that to a number, so that will return 0 or 1. And we'll get a hash whose keys are 0 and 1. And what will the values be? Well, the way classify works is the values will be all of the items from the original list that we were iterating over sorted into the key that corresponds to the return value for that item. So 1 will have all of the items where our predicate returned something that was cast to 1, that is all of the items where our predicate returned true, and 0 will have all of the items where our predicate returned false. So that has the effect of classifying our items, but we wanted them to be returned in a particular order to match the API of C++'s partition. So the problem that we would have with Raku is that not only are our hashes not guaranteed to be in insertion order, they are actually guaranteed to not be in any stable order at all to prevent subtle bugs from showing up later. So we can't count on the first key value pair being the items that passed our predicate and the second being the ones that failed, or vice versa. That means that to get a particular order, we need to actually index into the keys that we want. Fortunately, a multi-slice of all of the items with a key of 1 followed by all the items with a key of 0 makes that very easy and gets us a single list of a stably partitioned set of the elements that we started with. And now we have a series of functions dealing with permutations, which are definitely on the easier side of the functions we'll be implementing, but slightly non-intuitive, at least at first. And the part that I think is least intuitive about them is the implementation of isPermutation, which is actually in Raku all it takes is testing for set equality. Why is that enough to fully implement the C++ is permutation? Well, what it means for one list to be a permutation of another is that the two lists are the same but with different order. And what it means for two sets to be the same is to be equal is that they have the same members. So anything that is a permutation will pass set equality for a corresponding list. We can also implement next permutation a bit more intuitively. We just use the permutations method and look for the first item on it. And previous permutations, correspondingly, we take the last item in permutations. Of course, a slight difference in the API here is next permutation you could call again and again to iterate through permutations, whereas with our permutations method in Raku, you would get a collection and you would actually need to iterate through it yourself. But that has the advantage of where you are in the collection of permutations, which has some ergonomic advantages and disadvantages compared to being able to just call next with next permutation. But on the whole, I think is a good trade-off from expressiveness and ease of use perspective. All right, now we're getting into some that I find especially exciting to tell you about, both because they show off some of the features that make Raku so expressive and such a good match for implementing these sorts of functions, and because they demonstrate some of the difficulties that I think C++'s high level of abstraction here create. We're getting into several areas where the C++ algorithm function has a name that is expressive in terms of its default operation, but that does not really capture the full power of the function in question. And I think that lowering the level of abstraction the way Raku does really helps clarify some of these examples, but I'll point that out as we go through this slide. To do that, we're going to make use of the Ziptail, which I showed you before, which, just as a quick refresher, is the implementation I have here uses an anonymous method to zip a list together with a copy of itself where the first element has been skipped. Using that function, we can implement isSorted just by zipping together a list with Ziptail and then applying with zip as a meta operator the less than operator, which will get us a list not of pairs of items zipped together, but of just Booleans that tell us whether or not each item is less than the item that follows it. And of course, if every item is less than the item that follows it, then our list is correctly sorted in ascending order. So if all of those values are true, and we coerce that to a Boolean, and that returns true, then our list is sorted. If it returns false because not all of those were true, then our list was not sorted. And this allows us to implement isSorted. But note that if we want to test for something other than sorting, then because we have a transparent implementation here, you can see exactly where we're doing that comparison, and you can replace the less than operator with any operator or indeed any binary function that you'd like, and get that transparently without having to think about an operator overload or something that you can pass to isSorted that causes it to behave differently. All right, so we can do something very similar with isSortedUntil, except instead of directly passing our operator to zip as a meta operator, we will just do our normal Ziptail and get pairs, and then map over those pairs and test whether each item is sorted. And if it is, proceed on to the next. And if they're all sorted, then just sum up the count and say that it's sorted until the very end of the list. But if we ever get to a point where an item is not less than the following item that it's been paired up with, we need to bail out early, which Raku lets us do. Again, many map implementations would not let us bail out early in that way, because map in a pure functional language with a strong type system, map would be guaranteed to return a list of the same length. But we have a bit more flexibility than that in Raku, and we're allowed to return a shorter list if we want to, using last. So that's exactly what we do here. If our test ever fails, then the OR proceeds on to its second half, and last bails out early. Our map stops short, and then when we sum up the number of trues, we get a number that tells us exactly what index we reached with all of our items being sorted. All right, and next, again, adjacent difference is one of those sort of poorly, or at least incompletely named C++ algorithms. What it does is, in its default implementation, it tells you it's well named in its default implementation. It tells you what the difference between each adjacent pair of items in the list is. That is, what is the first item minus the second item. And that's exactly what this implementation does. Ziptail applying minus as our binary operator gives us the adjacent difference. However, the C++ adjacent difference can be used much more flexibly than that. It can be passed any other binary operator, and similarly, our Ziptail here can, of course, be passed any other binary operator. But unlike the C++ algorithm, which has the idea of its default operator encoded into a name that is confusing if you're passing it some other operation, here we have just a transparent description. And I don't point this out every time, but note here that we have something that is in fact shorter than the function it is replacing. So not only is it clearer, not only is it more transparent, it's actually more concise. So I think this is a really clear win for Raku. That the brevity point is not true for adjacent find, which is our next algorithm, but everything else that I just said is. We once again have a C++ algorithm that is named well for its default case, but is named confusingly for non-default usage. What adjacent find does by default is test elements and find the first repeated pair. So, if you have a list 1, 2, 3, 3, 4, it would say, oh, 3 is the first time that I found something that is the same as an adjacent element. And that's exactly what our implementation here does. We do our, by now, familiar Ziptail, and then look for the first pair where the adjacent elements are double equal to each other. We could use a different predicate if we were interested in a different sort of equality. And then that will give us that pair as the first. The return value from the first function will be the first pair that satisfies that predicate. But adjacent find is just interested in the actual first value. So to match that API, we then index into the pair and take its first item from the pair. And again, like adjacent find is clear in the default case, we are also clear we have that equals inside our reduce meta operator that makes it very explicit about what we're doing here. But we go a little bit further than that, because if we want to put a different operator in there, any binary predicate would work just fine, a different sort of equality or a custom function. It remains clear what we're doing, whereas in C++, you have sort of the cognitive dissonance, cognitive overhead of saying, well, adjacent find, except I'm overloading something, so it's not actually engaged in finding anything. Once again, I hope this is illustrating the value of transparency. All right, for this next batch of functions, we're going to not only need our now good friend Ziptail, but also the other building block helper function I introduced earlier, binaryfilter. So just a very quick refresher on that. That function is a function over two arrays or lists A and B, and A contains elements of interest, and B contains a binary list, a list of booleans, or boolean-like elements, and then we use B as a filter on A and remove all of the elements that are not, that correspond to a falsy value in B. We remove those from A, and every element that is at an index that has a truthy value in B, we keep that in A. Okay, so how can we use a binary filter to implement the C++ algorithm mismatch? Which, by the way, I know I've mentioned several poorly named C++ algorithms, but I have heard mismatch described as the single worst name in the C++ algorithm header. So what does mismatch even do? Well, mismatch, its default implementation anyway, takes two arrays and tells us, returns to us the first element that is not the same in the two arrays, the first time that there is a mismatch between the elements at the same index in those arrays. So how would we implement that? Well, we do our familiar zip, but instead of zipping with a list with its own tail, we zip these two different lists together. And then on our zip meta operator, we apply that to the not equal to, which, note what Raku is doing here, we have the triple equal to operator modified by the meta operator that negates binary operators, modified by the zip meta operator. So we have a meta operator, which is really Raku kind of showing off here. But in any event, that zipping those two lists together gets us a list of booleans, where we have false if the two arrays are equal, and true if the elements at the same index of the two arrays are equal. True if they are not equal, because of that negation there. So we have a list of booleans, and a list of booleans is exactly what we need for our binary filter. So we do that binary filter on A, which gives us a list that consists either of false or of the element that was not equal. And then we look for the first element in that array, because that will be the first mismatch, and that's our result. The first element that is not false. So why is this such a poorly named function in C++? It really does give us the first mismatch. Well, because that's just the default behavior. And looking for the first mismatch in two arrays is really not that useful. But mismatch is, in C++, a very useful algorithm, because you can overload the not equals operator and find all sorts of, have many more useful predicates to compare to arrays. But that is totally obscured by the abstraction and the black box of the name. Without checking the API docs, you don't necessarily know that from the name. Whereas looking at this function that we've written out here, you see exactly what it's doing and know just by looking at it, that you can put in a different operator instead of this equality operator or this not equality operator, and find whatever it is you're looking for. So once again, this transparency, I hope you're starting to see the value of it. All right, let's move on to the C++ algorithm isPartitioned. Before diving into an implementation, what does isPartition do? Well, a list is partitioned if it can be divided into a front half and a back half, and the front half should have everything pass a predicate, and the back half should have everything fail a predicate. So it's kind of like being sorted, but less strict. Let me just mention an example. So if you wanted to say, is a list partitioned on the predicate less than 5, then that would mean that the front portion of the list has items that are less than 5, and the back half, again, it shouldn't be half. We don't know how much, but the back portion of the list has elements that are not less than 5. So it's like sorting, but you don't know that everything is in ascending order. You just know that there's a portion of the list that passes and a portion that fails, and it doesn't flip-flop between the two. So let's take a look at how we implement that in Raku. So first we use our very good friend Ziptail, and we have a list of pairs, and then we map over that list, and we say, is there does the first element pass the predicate, and does the second element pass the predicate, fail the predicate? And if that is true, then that means that we're at a point where there is a sort of break, and that is our partition point. If that is less than or equal to 1, that means there should be 0 or 1 partition points in a correctly partitioned list, then isPartitioned is true. If that is 2 or more, then we know that there are multiple partition points, but that you can't have multiple partition points in a correctly partitioned array. So then that would return false. And that is exactly what isPartition does in C++. Note that this one is a bit verbose. I mean, I don't insist that these be absolutely shorter or anything than the C++ equivalent, but this one is getting a little long. So I don't tend to work with partition lists that often. If I did, this was the sort of length where I might start saving this in a helper function. But even so, it's nice to be able to see it just in one line and know what it is we're dealing with. C++ also offers the isPartitionedUntil, and that implementation in Raku is pretty much a carbon copy of isPartitioned, except instead of checking to see whether we have just a single partition point, we actually use our friend the binaryfilter, and then find the first place where that is, and that gives us the how long the partition goes, and we get that first item. Partition point is nearly the same, except instead of returning that item, we're going to return the index, which gives us the different access to the same information, essentially. And so those are all of C++'s partition-related algorithms. Okay, with this next slide, we're going to finish off the core C++ algorithms that we'll be covering. And the first function I want to do to talk about to do that is one that I'm very happy with the Raku implementation of, and that's inner product. The reason I like the Raku implementation of inner product so much is because I'm not really sure why. Maybe because my math education stopped with the second semester of calculus in undergrad, but I can never keep the order of operation straight for inner product, but I can keep it straight just fine with the Raku implementation, which is zip two lists together, multiplying each element, and then sum each of those multiplication results. So it's multiply and then add, and that is clear, just transparently obvious from the implementation. No need to check the documentation or type into a DuckDuckGo search what inner product is. And of course, if you want to apply different operations, it's exactly clear where you plug them in. Don't have to check the order for function overloads or anything like that. Transparency helps us out. The next operation from the algorithms header is exclusive scan, which is pretty much trivially implementable as a produce operation here, given the plus function, which is the default for exclusive scan, but we can pass it anything we want. This shows the power of Raku's slip operator. In many languages, you need an overloaded version of a produce or a reduce to be able to pass in a starting value or a default value. But with Raku, of course, we can just create a new list that consists of whatever starting value we want, with a slipped version of our starting list, which just easily appends that first item to the beginning of our list. Note that we do need to manually provide the correct identity value, which is, so if we're adding, as we are here, 0 is an identity value, but 0 is not an identity value for multiplication. The product of 0 and anything is 0, so we would need to supply 1 as the identity value there. There is that limitation to our implementation, but other than that, it is exclusive scan. The last two things that we're pulling from C++ implementations are fairly trivial, but I just want to mention them here for completeness. Transform reduce, which is just map reduce, and transform inclusive scan, which is just map followed by produce. Once again, C++ feels the need to break these out into separate operations to have to give the programmer fine-grained control over parallelism, but we implement the same thing by having the option to apply race or hyper to get parallel implementations of MapReduce or MapProduce. Now, if any of you have been even vaguely counting along, you might have been surprised to hear me say that we are to the end of the core algorithms from C++'s 105 algorithms in the algorithm header, because I'm not sure of the exact count, but we definitely haven't implemented 105. But I said we're to the end of the core because a lot of the actual numbers in the C++ algorithm header comes from what the video that I'm riffing off of described as secret runes, which are modifiers like copy, not, if, and in that are applied to sort of pad out the number of algorithms. So you may have something that sorts or in place versus a sort copy that returns a new copy. And the thing about those in the C++ algorithm header is, although they are relatively consistent in terms of providing these sort of alternate versions of their algorithms, they are consistent only by convention. someone had to manually implement a in-place version of an algorithm plus a copy version of an algorithm, and they, while pretty consistent to do so where it makes sense, they don't always, and so you have to look that up, and you don't get those for free. If you want to implement your own algorithms, you need to decide whether you're going to implement an in-place version, a copy version, or a both version. Raku takes a slightly different approach, and I think a better one here, in the same sort of compositional way we've been talking about. We have pretty much everything I have shown you so far has been a copy version, but we can compose that to do it in place with the dot equals meta operator. So, if we want to have a sort, instead of a dot sort, we can do a dot equals sort, and that will sort in place. We'll assign the new copy back to the original variable. Whether or not that counts as in place is a little bit debatable if you're looking at it from a pure memory efficiency point of view, but it's effectively in place from a variable assignment point of view. Similarly, as I've already mentioned, we have not only as a negation operator, but also as a binary meta operator. So anything that we can do as an operator, we can do a not version as a negated relational operator. And that gives us all of the not versions essentially for free. And if we have an if expression or a do if expression, or if you want to do something or something else with an else, the ternary also works. Ternary operator also works. And, in many C family languages, if can only be a statement, but by either using do if or just wrapping the if expression in parentheses, we can have that be an expression in Raku. So that allows us to just change the transparent implementation of any of the functions I showed before to have that conditional logic embedded directly in them. And similarly, because we can implement the in version, which limits the application of a function to a certain number of times by using last. A last always, unlike many languages that don't allow for short-circuiting, Raku is very free about allowing short-circuiting with last. And we have the concept of anonymous state variables. So, if you're mapping through a list, then $$ will always give you the current index that you're at. And if you want to just map through the first 10, you can just bail out with last whenever you get to index 10. And similarly with any other iteration construct in the language. So that gives us all of these sort of secret runes, as they're called in C++. It gives us all of those for free. So and this is part of the payoff from having this sort of more transparent approach to our function implementations. Because they are not black boxes, there's not that same abstraction barrier. We're free to stick an if or a not or a last right there in the inline implementation, and we are not dependent on a library author to have implemented that version of the function for us. We can just compose it ourselves right there inline transparently. So with that, we have finished all of the algorithms from the C++ algorithm header that I wanted to cover, but as I mentioned, there were a few that didn't seem quite right to include that dealt with heaps or a few that dealt with some low-level issues. So I do want to just make sure that I'm still getting to about the same number and include a few sort of bonus ones from outside the algorithm header and some from outside of C++, but that are good to know and show off some features of Raku that are helpful when thinking through this type of problem. The first is one that we've actually already seen you can do with the reverse method, but I also want you to see that you can combine the reduce meta operator and the reverse meta operator and the comma operator to achieve the same effect. You can just reverse an array with that, and I'm mentioning that in part because it's concise and handy and a nice idiom to know, and in part because we haven't talked about either the reverse operator or much about the reduce meta operator, both of which are good tools to have in your tool belt. I also want to show an implementation of all equal, which is a very handy test to see whether all of, just like it says, all of the elements in a list are equal to each other. And I'm mentioning this in part because it shows off the fact that operators, including the equality operator in Raku, can have what is called list associativity. Normally reduce, if it puts an operator between each element in an array, it wouldn't be able to tell you whether they're all equal, just whether equal returns true when shoved in between each element, which is not necessarily the same thing. But list associativity allows all equal to return true if and only if all of the elements in the list are in fact the same, which is something that very few other languages can implement quite as easily. So that's something I encourage you to dig into if you're interested in that sort of thing. Next, I want to show a couple of string operations. First, just to not forget the very good Unicode and regex support that Raku has. So it's pretty trivial to test whether a string is composed entirely of uppercase characters. Just does the beginning to the end consist of one or more uppercase characters and nothing else? And then to make that a Boolean test, cast it to a Boolean. And I could give you a whole page of things you could do with regex that would correspond to methods or functions that might be in another language. But the basic lesson here is anytime you have something, some sort of string operation, and you don't see a method for it in Raku, think for a second, is this something I could do with a pretty trivial regex? Next, I want to mention splitting a string at a particular index. In this example, we're splitting at 3. Note that although strings are not character arrays in Raku, they are easy to turn into a list of characters with comb, and then you can rotor or zip or do whatever you want, operate on them as a list, and then join them back into a string. So that string to list, do something with the list, back to string path is one that is a pattern that you should be aware of. And one that has many more applications than just split at. Here, the rotor implementation is saying, I want to turn this into a two-element list. The first should have 3 items in it, and the second should have everything other than 3. But you can obviously have the full power of Raku to list manipulation to deal with that list once you get the list of characters. And finally, for this slide, I want to mention the power of the sequence operator. The example here is take until, but the point that I'm making here is that we typically think of a sequence, the sequence operator operating over a list of items that it is generating itself, but note that if you already have a list, you can also use the sequence operator with that existing list. So here the list L could already have certain items in it, and the predicate would still apply. So, you know, if you want to say take until greater than 5 or take until is prime, or you know, whatever, you can apply that not only to a sequence that you're generating on the fly, but also to an already existing sequence, and use that to filter or otherwise manipulate the existing list. So that's another pattern to be aware of. And that is really all the algorithms I wanted to talk about. There are plenty more I could discuss, but in the interest of leaving at least a few minutes for questions, and because I think that's more than enough for one day, I'm going to stop with that, except to return one last time to the GitHub comment that I mentioned at the beginning of today's talk. It mentioned that there were a lot of algorithms missing from the Raku standard library, including standard deviation. And I certainly would be open to including something as complicated as standard deviation in the standard library. It is probably a bit much to define inline. But I also think that it is really worth celebrating how easy Raku makes it to define something like that inline in a expressive way. So here's how a mathematician would write the standard deviation formula, and here's how we'd write the same thing in Raku. Standard deviation is equal to the square root of 1 over the number of elements in an array times the sum of all of the elements in that array modified by taking each element in the array and subtracting the average of the elements in that array, all squared. And to me, that reads pretty well. I look forward to your questions. Thanks so much. All right. Well, thank you for sticking around for this presentation. I would love to have questions from anyone. I answered a few in the chat, but I'm happy to take any either by chat or if people would like to raise their hand to be unmuted. Well, I'll be best positioned to answer questions about my talk, but I'm certainly happy to have general questions as well. Let's see, Rob, it looks like you have your hand up. Andrew, are you unmuting people with questions, or I'm not doing that? Okay, Rob, go ahead.
Well, I'm not very advanced on Raku yet, and I find the star, the asterisk, confusing in some of your later presentation items. Like your exclusive scan. In the last bracket of that, you have a star -1, and the star seems to come up as a few different things in Raku, and I'm not really finding what it represents there.
Sure. So the star has two uses in, or well, two categories of uses in Raku. It is either a whatever or part of a whatever code expression. If it is a whatever, then it is being used to in some way that is sort of defined by the function that it is being passed as an argument to. But here in an exclusive scan, the way that is being used is as a whatever code. So it's star -1, which is evaluates to the expression of a whatever code, which is sort of whatever -1. There in the indexing context, the whatever code expression is called with the length of the array. So basically what that is saying is the length of the array -1, that is the last element of the array. And that's a pretty common idiom for any array indexing in Raku will have whatever as an alias to the list length, which allows for indexing from the back of an array. You know, many languages will actually just let you do, -1 to index to the element right before the end of the array, or -5 or whatever. But with Raku, they decided that it would be clearer to literally subtract from the length, but have whatever be a convenient alias for that length, rather than having supporting negative indices. There's a question in the chat. One property of the STL is that algorithms have specific big O complexity. What approach do you use to determine complexity of Raku one-liners? That is a good point, that these algorithms are, because there aren't like API docs to look up, you can't necessarily say what the algorithmic complexity is by like consulting documentation. The goal with having things be more transparent is because you can see the actual implementation, you can reason about the big O complexity. Of course, that requires knowing the big O complexity of sort of primitive operations built up into Raku. So if you know, oh, I'm iterating through this loop once with a map, you have to know that that is O of n complexity because you are iterating through the loop. But yeah, the idea is that you can look at them and reason about the algorithmic complexity by knowing things about the algorithmic complexity of the components that you are composing. Did that answer the question? All right, well, thank you, everyone. If there aren't any more questions, I guess we can go ahead and stop now and have just a couple minutes before the next talk. There was a last question. Can you talk about iterators more? Yeah, there's that link, and iterators as a C++ concept, I am certainly not an expert on, but they're a way of sort of iterating through iterable objects in terms of iterating on, in terms of iterators as a more general concept. I mentioned them as a Raku term just to refer to anything that can be iterated over. So a list, an array, anything that you can sort of hand to a for loop or a map to iterate over. Yeah, that's a good, from the chat, iterators are a superset of pointers in C++. Andrew Stepanov would probably, or Alexander Stepanov would probably call them coordinates if he redid the STL. I think that's a good way to put it. They are very layman's, my very layman's understanding of C++ iterators is that they are basically a type of pointer that points to where you are in an iterable collection. But they are used for a lot of areas where we would use a range or an array or a list. C++ is getting ranges, which will replace many of the, or will be another alternative for many of the ways that places they currently use iterators, if I understand correctly. Again, I'm not a C++ expert. All right, thanks everyone.